Hello everybody, welcome back to the next video of electrostatics. So today in this video we are going to talk about a fresh topic that is known as electric flux. Now what do you actually mean by electric flux? So electric flux are nothing but basically they are electric field lines that passes through a particular surface at a given amount of time. Okay, now what do you actually mean by that? And by time is an irrelevant factor here because we will be talking about flux that passes through a surface unilaterally. Okay, so let us understand what that actually means. Now, in order to understand this thing by an easy example, I can say it in this particular way. Suppose if there is a wall over here, okay, there is a wall over here and there is a particular window. Okay, there is a window in the wall. So, if there is a sun on the other side and there are some sun rays, okay, that is directed towards the wall. Okay, now of all the sun rays that will go and hit the wall, there will be few of the sun rays that will go through the window, right? So of all the sun rays, there are few of the sun rays that will go through the window. So those particular sun rays that can enter through this window surface will be termed as the light flux or intensity of light flux, which we are talking about here. The same situation can be recreated for electric flux as well. Let us try to understand how. So, in order to understand the concept of electric flux, let us take an example in this particular way. If I say we have some external field lines that is going in this particular direction and I place a particular surface in that region where these field lines are crossing. So let me take this to be a surface. Okay, so if I take this surface and if I place it here, now let me draw a few more field lines so as to make the example clear. Okay, now if I place it here, okay, if I place the surface somewhere here, so I can see out of all the field lines there are only 4 of them that passes through this surface, right? So these were the 4 that were passing through the surface when I place the surface here. So this particular field lines would be termed as electric flux. So by definition, electric flux is nothing but the field lines that passes through a given surface. So now let me just draw the surface over here so that we can understand it clearly, right? So this was the surface and this is where the field lines were crossing through. Now the expression for electric flux is given by the letter phi. So if I talk about small amount of flux, I can write it as d phi, and the formula wise, if I want to get the expression for d phi, it is given by the dot product of E and ds. Now let me make you understand what are these things. Here the letter capital E of course represents nothing but the field lines that passes through the given surface. So E is nothing but the electric field lines, and ds is actually the area vector. Now with that area vector you can also place an n cap, which is a unit vector that represents the direction of this particular area vector. So ds is known as the area vector. Now what do you actually mean by area vector? Okay, so let us again try to understand that thing. So when I talk about area vector, this is a vector quantity that is pretty particularly sure from the name itself, right? So if I take this to be a particular surface, so any area vector is nothing but a direction directed from that surface perpendicularly outward. That is what is meant by area vector. So if I say about this surface, for this surface, the area vector should be perpendicular to the surface and it should be directed outward, right? So for this surface, the area vector would be directed in this particular direction with the direction in the upward way. So if I take this surface in this particular side, hence the area vector would be directed in this particular direction, right? So area vector is nothing but the direction of that particular surface perpendicularly towards the outward region. Now taking that into concern, if I break this formula further down, because this is a dot product, so I can write it as EDS cos of theta. Now, what is this theta over here? This theta is nothing but the angle between the electric field and the area vector. Now, how do you determine that? in this particular case, we need to be particularly sure about what is this particular angle and how are we going to deal with this particular angle. Let us try to understand how. So, as you can see in the figure here, I have shaded the surface here. So, in order to understand the angle between the electric field and the area vector, all we need to know are the directions of the field and the area vector. So, if I consider this surface to be placed in this particular direction, okay, if I consider the surface to be placed in this particular direction, hence in this particular direction the area vector for this surface would also be directed outward. So the direction of the area vector or delta S would be in this particular direction, correct? So taking that direction into concern, electric field is also in this particular direction, delta is also in this particular direction. So the angle between them would be 0 degree. Considering 0 degree, this would be cos 0. Cos 0 is 1, hence the answer would be EDS, that would be d phi. And again, in order to get the complete flux or the total flux, I need to integrate these two quantities. So here, integrating the quantity, what I will get is the total flux, that is phi, and over here the integration would be for the surface. So for the total integration, I will get the area of the whole surface, so I can write it as A into A, right? If I consider A to be the total area of the surface. Now this is what is given for the expression of electric flux. So electric flux is given by the dot product of the electric field and the area vector, and theta, which comes out as cos theta because of the dot product, that theta is actually the angle between electric field and the area vector. Now let us try to understand what would happen if I do not apply a cross product if I do not apply a dot product. Instead of that, if I go for cross product, will I end up getting the same thing? Will the expression and the concept still remain the same? Now let us try to understand that particular point. So in place of dot product, if I try using cross product, then the flux would be given by E cross delta S, and that would be given by E delta S sine of theta. So in this case, if I now consider this particular example where I place the surface area in such a way that the angle between the area vector and the electric field is 0 degree. So I am getting the total field lines passing through the surface, but considering the theta to be 0 here, sine 0 will give us a value of 0. So this would finally result into 0, which is contradicting our concept, because if considering that particular angle, I should get all the field lines passing through the surface. But if the angle is considered to be 0 and if I apply sine theta, hence I will get the total flux to be 0, which is not the case. But now if I say in this particular way, suppose the electric field lines are passing in the same direction, but I am placing the surface in this particular way. So if I place the surface in this particular way, it's pretty clear from the situation itself that the field lines is not going to pass through the surface, because the surface is in this particular direction, the field lines are going in this particular direction, right? So the field lines are not going through the surface, hence I should not get any flux. That means the total flux should come out to be 0. So if I consider this situation, in this particular situation, the electric fields are going in this direction, but the direction of the area vector is in the upward direction. So let me draw it over here. The field lines are going in this particular direction. The direction of the area vector, I can also take it as delta S, it is in the upward direction. So the angle between them is 90 degree. So if I consider E delta S cos theta and E delta S sine theta, and if I consider theta to be 90 degree in both of the situation, we know cos 90 is 0, so I'll get this expression to be 0. But on the other hand, sine 90 gives us a value of 1, so this will come out as E delta S. So as I have already said in the situation, the field lines passing through a surface in this particular situation is 0, so flux should come out as 0. But in this case, the dot product is giving us a 0 value, but the cross product is not giving us a 0 value. Hence, the correct expression for flux is not represented by cross product. It has to be, in any situation, should be represented by dot product. So that has to be kept in mind for any kind of situation. Let us now discuss about the units and the dimension for electric flux. So from the expression itself, we can determine the unit as well as its dimension, which is pretty simple. So the unit for electric field and area vector will give us a unit for electric flux as well. So for electric field we can use the unit as Newton per coulomb into, for area obviously it's meter square. So it's Newton per coulomb into meter square. So how do we get Newton per coulomb? If we do not remember that particular formula, I am just stating it. For any electrostatic force, we can write down the expression as force as F equals to charge multiplied by electric field. So from here, if I write down the expression for electric field, that will be given by F by Q. So the unit for force is Newton, the unit for force is Coulomb. So hence, the unit for electric field is given by Newton per Coulomb. So as a whole, the unit for flux would be given by Newton per Coulomb into meter square. So that would be the unit for flux. We can also further break it down into other SI terms by breaking Newton into kg meter per second square and so on. So, but this would stand as the particular unit for flux. Now let us discuss the dimension as well. So for dimension as well, we are going to take help from the formula. So from the formula itself, it's electric field multiplied by area. So first we need to find out the dimension for field, and then we can find out the dimension for area, and multiplying both we can get the dimension for flux. So that would be given by force. So what is the dimension? So it's Newton per coulomb into meter square, right? So you just substitute the dimension one by one for each of the following terms and you'll get the final dimension as a whole. So Newton is actually the unit for force, so we need to substitute the dimension for force. So force is given by mass into acceleration, mass is given by m, acceleration is given by meter per second square, so that would be L t to the power minus 2. So the dimension for force would be m L t to the power minus 2, m L t to the power minus 2, divided by Coulomb. Coulomb is the unit of charge. The charge Q is given by I into T, current multiplied by time. The dimension for current is taken as ampere and for time it is taken as T. So for charge or for Coulomb, we'll take it as A into T. A into T. And for meter square, obviously it would be L square. So if I multiply it all throughout, I'll get it as M L cube T to the power minus 3 into A. M L cube T to the power minus 3 into A to the power minus 1. So that would be the dimension for electric